In this video, I wanted to address some issues that are tough to do so in a whole class setting because we're dealing with details, and I think it's important to take some time to address them in the context of this kind of format. So what I want to talk about is what are some of the challenges or wrinkles we encounter when solving linear systems algebraically. We spend a good deal of time looking at linear systems graphically. It's really useful to be able to see whether lines intersect in space and where they intersect, and be able to kind of point out their solutions. At the same time, graphing systems has its shortcomings. It's pretty labor intensive. If the solutions are not happening at integer values, then it's really tough to see them. Or if they're happening at places on the graph that are not convenient, like gigantic ordered pairs, 100, 300. Really tough to kind of get a sense of that when you're graphing. So we've decided to kind of move and shift towards solving algebraically, but there are some things that we should address. So I have some problems solved that I'm going to be narrating for you in the next few minutes. Here are some of the things we're going to encounter along the way. So one of the first things we'll encounter is if I'm solving a system algebraically, how do I just manipulate one equation of that system to facilitate substitution? If substitution is what I want to do, is it possible just to manipulate one equation of the system in order to do that? And the answer is yes. Another point that I want to address is how do we make sense of variables other than the traditional XY pairing? So what happens if I have different variables? How do I deal with them? How do I make sense of them? Another issue is how do we take combination elimination, which is really the act of combining equations either using addition or subtraction? How can this combination elimination be set in motion by modifying one or more of the equations algebraically? Sometimes it's sufficient to change one equation of a system. Sometimes it's necessary to change both of them to create opportunities for elimination where one of the variables is being canceled out. And finally, these last 2 points. If I'm solving a system algebraically, is it possible, even though I don't have a graph in front of me, to tell that that particular system has no solution? And what do those outcomes look like? Or conversely, what does it look like if that system has infinitely many solutions? What am I looking for? What are some of the clues that tell me, hey, whatever system I'm solving has these outcomes? Because again, I don't have anything graphical to lean on. So let's actually look at some of these problems and see what we can make sense of. And these are problems that I grabbed out of a textbook, and each one of them has some value for us here. So let's start with this system here. You notice that I don't have the traditional XY values. I have the letters C and D instead. Both of these equations are linear. They're in standard form. None of that really matters, though. What matters is that I wanted to take the substitution root. And what I'm noticing is that none of the variables has a coefficient of 1. Right? Normally you like to see a variable with a coefficient of 1. It's kind of easy then to solve for that variable and isolate it and then sub that value into another equation. That's the very essence of substitution. But here, that setup has not yet been created. However, if I take this second equation, let's call this equation 1 and equation 2. If I take this second equation here, I've taken equation 2 here, and I'm dividing the entire equation by 2, some cool things happen here. One of them is that the 2's cancel out, leaving me with C plus 3D. 6D divided by 2 is 3D, and negative 34 divided by 2 is negative 17. And that's convenient for me because now this variable has a coefficient of 1, and I can isolate it such that I can get C is equal to negative 3D minus 17. Now why is that useful? Because I can now take that other name for the letter C, right? I like to think of this as a synonym for C. I can also call the letter C negative 3D minus 17. I can now use substitution. Think about what just happened here. I manipulated, let's say I call this equation A and I call this equation B. I manipulated equation B. I didn't change what it means, I didn't change what it represents, but I changed the way it looked. So now it's written in terms of C, and I take that name for C and I plug it into equation A, which used to say 3 times C, but now it says 3 times this other name for C, negative 3D minus 17. And why is this to my advantage to be able to do this? Well, because now this equation has just one variable in it, and that variable is the letter D, in any equation like this, first degree equation, where all the powers of the variables are 1, where there's only one variable, it's very likely that I'm going to be able to isolate that variable and solve for it. So if you kind of follow through the math, I don't feel like there's a need for me to go through step by step, but I'm distributing here, combining like terms of negative 90 and negative 70. I find that D is equal to negative 3. And that's half of the story. Of course, when I'm solving a system, I want to find an ordered pair in space. I want to find out exactly where and if they intersect. So now I can take this value of D and I can plug it in into either equation that I choose. I could plug it into equation A or B, or even this version, let's call this version C. I can plug it into any one of these versions. I've kind of elected to plug it into version B, which used to say 2C plus 6D right here is equal to negative 34. But now I'm replacing that D value with negative 3, and I'm able to figure out that C is equal to negative 8. And so notice that when I report my answer, I do so in alphabetical order, just as I would with some X, Y pairing. Here the letter C precedes the letter D, so I report the answer as negative 8, comma negative 3. This is a consistent system because it has a solution and it's independent. Okay, so consistent meaning it has a solution of some sort, independent meaning it has one discrete solution. So I was able to manipulate one equation, isolate one variable, use that variable to plug it into the other equation. That's really the crux of what substitution is and what substitution looks like. In this next problem, it's the same exact system, but I'm taking a different approach. And this is one of the reasons that I don't want to be spending a lot of time in class doing mathematics while you watch. I'd rather you do mathematics and kind of get messy with it. But here I'm trying to show you that you can solve the same exact system but using a totally different strategy. Now I'm not using substitution anymore. Now I've decided to use combination elimination, and I've got some notes for you. Here again, not only do none of the variables have a leading coefficient of 1, but if I want to use combination elimination, you like to have matching coefficients, and none of them match. The C's have different coefficients, as do the D's. So I've written here, none of the coefficients match. And so combination right now won't lead to elimination. But if we manipulate the equations, and in this instance I chose to manipulate both of them. I chose to multiply the first equation, let's call it A. I chose to multiply it by the number 2, and I chose to multiply the second equation by the number 3. And in doing so, you might say, well, where did those values come from? That seems totally random. But it wasn't. I wanted the leading coefficients to end up being 6. So I was targeting the variable C. And so I've got 6C here and a 6C here. And of course, I have to multiply everything in this first equation by 2 and everything in this second equation by 3. But what I end up with here are two equations where the leading coefficients match. I have the choice. Do I want to add these two equations or do I want to subtract them? I've chosen to subtract them so that 6C and 6C will cancel out. And you can see here that as I'm moving along combining these equations, I find that the value of D is negative 3. We saw that in the previous problem. Remember when we solved using substitution and I wrote, we know where this is going, right? I've shown you what I want to show you, that I didn't have to solve the system. I realize I'm not finished here, but you hopefully get my point, that I didn't have to solve the system using substitution. I can use a different avenue. And it's a beautiful thing to kind of have these options when solving these systems, that it's whatever structure you see, you can elect to take advantage of. Here's the same system, third time in a row, right? Same exact system, except this time, once more I want to use combination elimination, but rather than manipulate both equations, I've chosen just to manipulate one. I decided to multiply the second equation only by 3 over 2. And again, why? Why did I make that decision? Because I knew that in multiplying it by 3 over 2, okay, this is really 2 over 1, these 2's cancel out, leaving me with 3C. Of course, I'm multiplying everything by 3/2, not just that first value. And so I end up with the first equation not being changed at all. The second equation has been altered. The way it looks has been altered, but the values of C and D have not. And now I'm able to cancel out these C's. And here I go again, successfully finding that D has a value of negative 3. allowing me to kind of go ahead and search out the value of c next if I so choose to. So you just kind of watched me solve the same system 3 different ways. The first time using substitution, the second and third times using combination elimination, and really kind of using a variety of strategies to do so. So we know that there's these different algebraic techniques. How do we recognize outcomes that are a little bit abnormal? How do we make sense of them without having a graph there to refer to? Well, here's a nice system to illustrate that point. Now I can move faster as far as what I'm doing because you've become much more familiar. I've taken this first equation. Notice that this q has a leading coefficient, or a coefficient I should say, not a leading, but coefficient of 1. And I've decided to isolate this or isolate this particular q so that I'm subtracting 7 from both sides, and this equation becomes this one. Q is equal to 2p minus 7. Now I'm using substitution to take this name for q and plug it into the second equation. And so you'll notice as I'm doing the math, suddenly all the math is correct. I'm following the rules of algebra with great fidelity. I get this kind of bizarre outcome. There are no mathematical errors. There's no faults in my logic. But I end up with this bizarre statement of 21 clearly not being equal to 24. And if my mathematics is correct, and if my logic and reasoning are sound, then I can safely interpret this as meaning that there is going to be no solution. Why? Because there is no ordered pair. There's no ordered pair for P and Q that simultaneously makes both systems true. And that's what this is telling you numerically. So frequently, if not always, if you get an outcome like this, where you're getting some numerical value not being equal to another numerical value, you can safely assume that there is no solution to that system. What's happening here? You've got 2 lines that are likely parallel in space, so that there is no chance of them intersecting. There is no ordered pair that satisfies them both. So that's what a no solution looks like. Here's another kind of flavor for what no solution looks like. Same exact system again, but this person, and it's me I guess in this case, has decided to take a different approach. And this time the approach is multiplying the first equation by 3 so that I can use some combination elimination. I'm targeting these p-values here. Again, here I am multiplying the first equation by 3, everything. And the p's cancel out, and I get the q's canceling out, ending up with 0 not being equal to -3. Okay, it's not the same numerical outcome I had before, but it's the same conclusion. There is no solution. There's no time when 0 is going to be equal to -3. So I don't need a graph to interpret what's happening. This system is a system made up of 2 lines that are parallel in space. They are never destined to meet. Which takes us to our final example. Here I have a system that looks pretty benign. Doesn't look like it's particularly scary at the outset. And the approach I've taken is to try to use some substitution. I kind of took advantage of the fact that this y has a coefficient of 1. Here I've solved for y, and so I've got another name or a synonym for y. I'm plugging this name for y into that first equation, and suddenly I get an outcome that's kind of perplexing. I get this outcome, that 2x plus 48 is equal to 2x plus 48. Now, it does not matter what numerical value I choose for x here because it's the same here, and the 2 sides of this equation are always going to be equal. In other words, if I let x equal 1, for instance, I'm going to find that I get 2 plus 48 equaling 2 plus 48, or 50 equaling 50, and that's true 100% of the time. So what's happening here? Well, there are infinitely many solutions. Forgive the poor writing, but I just kind of want to make the point that there are infinitely many solutions. Why? Because these are in fact the same exact line. They just look different from one another. They are the same line in space, but they have been manipulated in such a way that they appear different. So over the course of this video, you saw quite a bit, a lot of detail-oriented things, but I hope that it was helpful in kind of drawing your attention to some things that are tough to address in class with 30 different folks gathered together, and all of them kind of thinking about things in a slightly different way. So I do appreciate you watching. and see you in class.